This video covered basics of transformers theoretically. From self-attention to multi-head attention and positional encoding, I explained how self-attention and multi-head attention allows a model to focus on different parts of the input sequence and capture relationship between words, enabling it to understand context and dependencies more effectively. The video is a prerequisite for this video, so if you are not familiar about working of these, I strongly recommend you to watch that first. Note, there are several videos and tutorial for PyTorch implementation on the internet and very few with the TensorFlow. That's why I am proceeding with the TensorFlow for this entire series. Now let's begin with this video. Import packages to make your desired recipe. Set memory growth to true so that TensorFlow consumes memory as its need, else it will consume all of your memory at once. Load the dataset. To download the same dataset, you can use the link in the description. Split the dataset to training and testing part and load the train and label separately. Define some variables like maximum length of the sequence for embedding, dimension of embedding, how much attention units you want, and the number of classes, which are 2, positive and negative. Now let's make the self-attention layer. We know that the 3 important components of attention, query, key, and value, and they are learnable parameters. Let's implement this equation. The self-attention class implements the self-attention mechanism during initialization. The class takes parameter attention units to specify the dimensionality of the attention vectors. The build method is called when the layer is first used, and it defines the trainable weights for the attention mechanism. It creates weight matrices like WQ, WK, and WV corresponding to query, key, and value with the shape, input dimension, and attention units, where the input dimension is dimensionality of input tensor. In the call method, the input tensor is multiplied with the weight matrices to obtain the query, key, and value vectors respectively. The dimensionality of key vectors is calculated and used to scale the dot product between query and key by dividing it with the square root of dimension of model as represented in the equation. The scaled dot product attention is passed through a softmax activation function along the last axis to obtain the attention weights. Finally, the attention weights are multiplied with the value vector to obtain the output representation, which is returned along the attention weights. Now we have attention layer. It's time to make classifier. The model architecture consists of following layers: an embedding layer that maps the input indices to dense embedding vector, a positional encoding layer that applies sinusoidal encoding to the input sequence to provide positional information, a self-attention layer that performs a scale dot product attention on the encoded input sequence, a global average pooling layer that computes the average of attention weighted representation along that sequence dimension, a dense layer with ReLU activation to transform the pooled representation, a dropout layer to prevent overfitting, a dense layer with softmax activation for final classification. The call method defines the forward pass of the model. It applies the embedding layer to the input, scale the embedding values, add the positional encoding, and pass the result to the self-attention layer. The averaged representation is passed through a dense layer and dropout regularization. Finally, the output is fed into dense layer with softmax activation, which produces the predicted probabilities for each sentiment class. The positional encoding method generates positional encoding values using sine and cosine function based on the position and dimensionality of the input vectors. Generate angle rates using this part of the equation, then calculate the other remaining part. Now calculate sine for even indices and cosine wave for odd indices. You will need tokenization of words, and you can use Keras tokenizer to do that. This will create text to sequence of tokens and pad them with zeros to get a fixed length vector for both training and test dataset. Create an instance of label encoder and encode the string type labels to integers. Now use TensorFlow dataset to create a dataset pipeline for both training and test dataset. Create an instance of classifier by passing the required parameters. Create instance of loss function and gradient descent optimizer. Now we have everything ready to train the model. Define the number of epoch you want to train the model. For each epoch, get the dataset in batch, and with the gradient tape, feed the batch in classifier and get the output. Use loss function to calculate the loss. Now use gradient tape to calculate the gradient and use optimizer to update the model parameters. You can monitor the performance by printing it to output console. Training will take a bit of time, but not that much because the dataset is short. The training is finished. Write a function to measure the accuracy on the datasets. Define variables to store the count of correct prediction and total prediction. For each batch of the dataset, feed the batch into classifier and get the correct prediction. Divide it by total prediction to get the accuracy. Now use the function to get the accuracy on both training and test dataset. It's a good performance with little bit of overfitting, but that doesn't matter for this case. We need to understand the attention. So let's write the function to visualize the attention weight to know which part of the input the model paid attention to. Collect the attention weights by feeding an input to the model. Get the 2D output of attention weights. Convert the tokens back to words to plot on X and Y axis. Create a subplot and plot attention weights on a heat map. Set title, ticks, and plot it on notebook. Choose a sample from the dataset and use visualize function to see the heat map. And see, but you can't because the plot is too short for the sample. Let's plot another small sample. And now here's the visualization of what attention layer paid attention to. As you can see how group, makers, re and unite influences a lot, which is the significance of the self-attention. So here are 3 things you can remember from this video. Self-attention allows the model to focus on different parts of input sequence and capture relationship between words, enabling it to understand context and dependencies more effectively. Positional encoding retains the order of word and eliminating the need of recurrent neural networks. Visualize the attention weight to understand which part of the input the model pays most attention to. This visualization helps in interpreting the significance of self-attention and provides insight into how the model processes the input sequence. Makes easy to debug because you can actually see if the model paying attention to right words or not. That's all for the first video in the series. In the next video of the series, we'll be building full-fledged transformers for language translation using multi-head attention. Questions, suggestions, doubts, and improvements, let me know in the comments. Stay tuned to Instagram for more updates. And as always, thanks for watching.